Welcome to online lecture number 15. So, in the previous session, we had discussed about the gate level modeling fundamentals and the gate level modeling delay concepts with a Xilinx simulation. And we also learned about how to simulate a gate level modeling code, taking an example of full adder, ripple carry full adder, right? Ripple carry adder, 4-bit ripple carry adder. So that example I had taken, and also we took an example of delay based example, and we had one more example on mux to explore the constructs of gate level modeling. So in this session the plan is like we have 3 to 4 problem statements chosen, and of course I'll just help you in the questions. If you have any, if you ask me any question like how to write a code for respective question, I'll help you to write a code on the gate level using the gate level modeling. Okay, this is a plan. And concluding remarks on unit 2. The very first problem of the focus in today's session is the logic diagram of the RS latch with delay is shown below. So this is the RS latch, reset and set latch it is. When it is NOR, reset comes over here, set comes here. When it is NAND, it is set bar, reset bar, SR bar, R bar, latch. So that concept you already know. Okay. So this is a NOR gate, and they have mentioned that the delay specified for that particular NOR gate is 1, and similarly the next OR gate, the same delay is specified, that is 1 time units. Reset, set are the 2 inputs, Q bar are the 2 outputs. So what you need to do, write the Verilog description for the RS latch. That we can do. Include delays of 1 unit when instantiating the NOR gates. So that also will do it. Then write the stimulus module for the RS latch using the following table and verify the outputs. So here in detail code I'll definitely not help you, because by now you'll be able to write it, but here I'll just write one pseudocode. Okay. So first is module description. So module, let me write the module description here. Module RS latch, describe the inputs outputs. Let me describe the output first. Output is Q and Q bar. What about inputs? Remove the bracket, put the just colon, comma. Input is, let me call it as yes and R rather than reset and set. Okay. Close the bracket and semicolon. So there are no intermediates here, so no intermediates required. So directly you can start writing the code using gate level style of modeling. The gate level style of modeling is the constructs you need to use is NOR. Let me write the NOR. This is a Verilog construct. Let me label it, which is optional. So before the label, there should be something in between. So what is that? There should be a delay. So the delay, 1 second. Yeah, the delay I'll just mention it here. Hash into the bracket 1 followed by label. So this is how we need to mention between the Verilog construct primitive and the label to it, instantiation label. In between you need to write the delay, followed by output first. What is the output of the first one? Q. What are the inputs? First input is reset, I have named it as R. Second input is Q bar. Let me write it as Q bar. Semicolon. Similarly, next NOR gate I'll consider NOR hash 1, because it is also having 1 time units delay. Let me label it as N2. This is N1. This is N2. Okay. So what is the output of N2 NOR gate? It is Q bar. So what are the inputs? Input is you can have any inputs, right? Let me write S first, then Q. So Q. That's it. AND module. Okay. So this is your code for RS latch. Simple code. But this is not at over because they have asked us to write the stimulus block. So in stimulus block, what you do, we will write it in this way. Module stimulus. So here all the input should be mentioned with registers. What are those? S and R. Let me write in the same name. And all the output should be wires. That is Q and Q bar. And then you need to instantiate the design block. This is a design block. What is the name of the design block? RS latch. Let me write it. RS latch. RS latch. Let me label it as R1. So it is optional. You can have it or you may not have it. Followed by um, follow the order. So first order is Q, Q bar and all. Same thing I'll write it here because here also I have written the same thing. Q, Q bar, yes, R. So instantiation is done with a module stimulus, then followed by initial block, begin. So initially what shall I set? I shall set after, I can say 10 time units. Let me set S is equal to 0, R is equal to 0. That's it. Okay. This is the initial value. After 10, let me write it here. After next 10 times, yes, I'll keep it at 0. R, I'll keep it at 1. After another 10 time units, S is made as 1, R is made as 0. Next 10 time units, S is made as 1, R is made as 1. Both are made as 1. Next 10 time units, use a system task called dollar symbol finish. Semicolon. End module. That's it. Okay. So this is a module stimulus. I hope the things are clear. You can just write it by yourself. Okay. Any doubts if you have, you can definitely ping in the or put a message in the Gmeet chat box. Very simple. Next is design a 2:1 mux using buffif 0 and buffif 1 gates as shown below. This circuit diagram I may not ask in the exam. Still you should be able to write. Okay, just observe this question. They have asked us to design 2:1 mux using buffif 0, buffif 1. It's not mandatory to give this circuit diagram because you should design by yourself. Let me just tell you. So buffif, what is the work of buffif? 1. So when the control unit is 1, it will transfer the logic at its input to the output. So now think that S is equal to 1. When S is equal to 1, so this I in 1 comes at output. Let me write it here. The truth table. The truth table goes like this. S is a select line and this is your output. Okay. So when S is 0, think that when S is 0, so when S is 0, so here I'll get it as a 0. Here after bubble I get it as 1. Okay. After bubble I get it as 1, or else I can say let us not confuse, just you can say that S is 0, so it is buffif 0. Buffif 0. So buffif 0 will transmit the input to the output when it is 0. So in this case what happens is when S is set to 0, your logic will come out from this one. This is connected. Okay, so you get the output as in 0. Okay, similarly, if I give the logic 1, then here also I'll get 1, here also I'll get 1. But this time B2 will be transmitted. So in 1 will be transferred to the output. So when S is equal to 1, you will get in 1. So this is a logic for the mux, and it is acting as a 2:1 mux. Now we shall write the code for it. For writing the code, you need to take into the consideration the delay specification. For the gate B1 and B2, the delay specifications are same. Here, the rise delay is 1, 2 and 3 based on minimum, typical and maximum delay specification. Similarly, fall delays 3, 4 and 5, turn off delays 5, 6 and 7. Okay. So let me write a code for it. Module, module. So let me name it as mux 2_1 output. What are the output for this? I'm having only one output, that is out. Let me write it as out. What are the inputs? I'm having three inputs, in 0, in 1, then yes. So these are the inputs and outputs. No intermediates are needed because simple code it has. Now I call upon the first one, buffif 0. Buffif 0. B1 is a label, but before B1 I need to have the delay specification. That delay specification let me write. Hash, just carefully observe, the very first place, rise delay, fall delay, turn off delay are separated by commas, right? Are separated by commas. Whereas minimum delay, typical delay and maximum delay are separated by colon. So let me write the rise delay first. Rise delay is 1, colon, 2, colon, 3. Rise delay things are over, comma. Next comes fall delay. 3, colon, 4, colon, 5. Next comes turn off delay. Turn off delay is 5, colon, 5, colon, 6, colon, 7. So this is the delay specification followed by its label. Let me write the label first, B1. Followed by, write down the output first. What is the output here? Out. Next comes the input. This is the order you need to compulsorily follow. Next comes in 0. What is next? Control. What is the control? Yes. That's it. This is the first statement. Now similarly, the second statement is buffif 1 hash, same thing, because I mentioned that delay specification for gate B1 and B2 are same. Let me write the same thing. 1 colon 3 comma 3 colon 4 colon 5 comma 5 colon 6 colon 7, close the bracket. This is the delay specification followed by B2 is the label, followed by what is output? Output is out here also. You can see here also it is out, comma, followed by in 1, comma, select lines, common select line. So end module. Okay, so that's it. This is how you need to write the code for buffif 1 and buffif 0. And the rest of the code, that is apply the stimulus and test the output values. So this part I'll give you as a task for you. You need to write the stimulus block. Very simple. Module stimulus and inputs are declared as registers, reg in 0, in 1, yes, and outputs are declared as wire out. Then instantiate this one, So mux 2 underscore 1, write down out I in 0, I in 1, yes, follow the order. Followed by use the initial statement. After 10, begin, after 10 time units, force the values. Next, after 10 time units, again force the values. So by doing this, you will have a stimulus and end it with a dollar symbol finish. System task end module that completes your the code of stimulus. That I hope you will do it by yourself. Okay. So, well, shall I feel that there is no doubt in it. So we shall go to the next case. Just observe this problem statement carefully. Here we are going to explore the ways to implement 4-bit comparator. 4-bit comparator using 4-bit full adder. So this is quite, new thing for you, I guess. So we are designing 4-bit comparator using 4-bit full adder using structural style of modeling. So this is what we will do now. See here. So before I proceed, you just hear when think that I'm having two inputs, x and y are the two inputs, and I'm adding it. I'm adding it to get some answer. So if x is greater than y, what happens? That is x minus y. If I do this, I'll get the answer greater than 0. Okay, so means if x is, to analyze this, what I do is I subtract y with x. By this I can imply that x is greater than y. To do so, this operation I'll do it in the other way, that is plus x plus minus y, right? This should be greater than 0. That's it. So means I want to perform this subtraction using addition itself. How to do it? By taking the ones complement. So this is nothing but ones complement of y. So x added with ones complement of y should result in the answer greater than 0. So if that comes, then I'll decide by the comparison that x is greater than y. That's it. Okay. So similarly, if I want to have the analysis of x less than y, then what I do? Same thing I'll do it. This should result in less than 0. Then how it should be done? This means x is less than y. That's the meaning. How to be done? So this operation will perform it as same thing. Let me write it in this manner because it's a ones complement to y. So this should result in less than 0. This is case 2. Then case 3, x equal to y, how it is analyzed? When x is subtracted by y, it should be 0. It should be 0. So this implies x is equal to y, means x added with its y's complement, then it should result in I can say when we add it, it will result in all ones. Let me just take few more explanation on it. So this I call it as case 1. This I call it as case 2. This I call it as case 3. Okay. Let me consider case 1 first. Case 1. What does case 1 says? So case 1, x greater than y. So here let me assume x to be 1, 0, 0, 0. Okay. Then y to be um, 0 1 0 1. This is y. Okay. To be accurate, it is in decimal, it is 8 and it is 5, and you know that it is x greater than y because you will get it as 3. Now what I do is same thing. I'll retain x. X is as it is 1 0 0 0. This y is, I'll take its complement, so you get it as 1 0 1 0. So this is 1's complement. Now I add it because 1's complement is already taken, so this is done. So I need to add it. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0. You'll get a carry overflow. You'll get a carry overflow. So this carry overflow, what I do is, to get the right answer, this should be added to, one's complement, you know it. This should be added to 1 and you will get it as 0 0 1 1 and you will get it as 3. So this is for getting the answer. But for my analysis, what I do is if I get this carry, this is very important for me. So by this analysis, what I'm saying is if carry generates, carry generates, then what is the conclusion? Then x is greater than y. Okay, so let me write it here. If carry is equal to 1. This is the first case. Now similarly, second case we'll explore. I'll take the next slide for it. So case 2, x less than y. X, I'll take it as 1 0 0 0, which is nothing but 8. Next, y is nothing but let me take uh, whatever, yeah, 0. Same thing I'll take 0 1 0 1. I should have taken less than, right? So I'll reverse it. This I'll call it as y. This I'll call it as x. This is fine. I'll reverse the previous case. Now I should get it as minus 3. So what I do is x is equal to 0 1 0 1. Y is equal to, take its complement, y bar, 0 1 1 1. I'll add it. So there is no carry. So there is no carry here. Let us not worry about it because if to take it minus 3, there is no carry. If you take its 2's complement, if you take its 2's complement, you'll get the right answer. That is not our concern. So here there is no carry. Two things observation. One is there is no carry, and there is one more observation is done here. So this observation is what we'll write it. We'll come to it after analyzing case 3. So what is case 3? Case is x equal to y. Let me consider x also as x is equal to y is equal to 1 0 0 0. So both are same. Now what I do is x is equal to 1 0 0 0. Y is also 1 0 0 0. So I'll complement it. So I'll get it as 0 1 1 1. So when I add it, I'll get all ones. Means when you get all ones, then x is equal to y. That's the conclusion. Here, if no carry, and no all ones, then x is less than y. This is the logic. Simple logic. Okay. So very simple logic. So for that purpose, what we do is now we just write a truth table here. Like the truth table is we analyzed x greater than y, we analyzed x equal to y, okay, and by that By that we can find out y, x less than y by default. Because if this is 0, if this is 1, this is 0. If this is 1, this is 0, this is 0. If both are 0, then it should be 1. And there is one more case. This cannot be possible at all. It is not possible at all. But even if it is possible, then it should be kept 0. So in this case, if you analyze, so for 0, 0, 1, rest every case it is 0, 0, 0. Means it is a NOR gate. So NOR gate. So NORing of simple these two things will get me the x less than y. So with this fundamental, we shall proceed with the logic diagram. So the logic diagram looks like this. Initially, the same full adder I have taken, the full adder, 4-bit full adder that I had explained you earlier, same full adder. Here what I do is, I need to force a complement of y. A is equated with x, b is equated with y. So the second input I'll complement. So what I do is, I introduce a NOT gate here, NOT gate here, NOT gate here, NOT gate here. So force the complement of it. Then at the output, it is very careful. You should be very careful. If you get the carry output, then it is as good as your x is greater than y. Finish. Whenever you get a carry output, because carry output you will be getting only when x is greater than y. That we have seen. X equal to y and x less than y will not generate the carry. So this is decided. Done. Now next is case 3, that is equal to. When x is equal to y, when all the sum expressions are equal to 1. So I'll take all these things, whether all these are equal to 1 or not. To analyze that, I'll take all these and I'll put a AND gate. And this is x equal to y. X equal to y. Now x equal to y is done, x greater than y is done. Now I'll take the output of x equal to y, I'll take the output of x greater than y, and then I'll put a NOR gate to get x less than y. So this is the logic, very simple. Okay, so now this thing we shall try to do it in the what I can say, Xilinx environment, and this is our last topic of this chapter. You can have any number of such examples. So let me keep it. So I have not written the code of it. Just no, I need to write it now. So the code of full adder, ripple carry full adder is already there. This you already know. Now what we do is we design a comparator. Okay. Right click, new, Verilog module. So I write comparator. Okay, 4-bit comparator. Let it be just comparator. Enter. What are the inputs of the comparator? A, comma B are my inputs. So I'll take the bus MSB 3, LSB 0, because 4-bit it is 4-bit comparator. What are the outputs? A, GB, A greater than B. It's the first input. A equal to B, A less than B. These all are outputs of single bit. Next, finish. Okay, so now you have the comparator outputs, inputs and outputs. Now what I do is I start writing the code. So here, to start writing the code, let me analyze whether any intermediates are needed. So here there is no intermediate needed. Directly carry out is x greater than b. Here all the sum expressions whatever I get, that I'll feed it as the input at AND gate, whatever I get at the output. So that I'll collect it and I'll just use it for the generating x, e, y. So there is 4 intermediates here. and this XEY itself I'll feed it here, the XGY itself I'll feed it here, no intermediates needed. So only these four intermediates are needed for me. So for that, what I do is I'll take wire, I'll name it as S0, S1, S2, S3. So these are the intermediates. Now I call upon 4-bit ripple carry adder. So this 4-bit ripple carry adder, so what I do is, one second. Each single bit I need, yes, yeah. So I just switch over here. So this is a 4-bit ripple carry adder. So I'll copy down this for instantiation. So I'll instantiate it now. 4 add full. Let me label it as F1. Sum C out A B C in. So this one should be replaced. Sum is replaced by let me write this as just S. So S0, S1, S2, S3 can be written in terms of vectors. How it should be written? Wire 3 down to 0. Yes. So this yes, I'll write it here. Okay. That's the output of the full adder. Okay. So what are the inputs? Carry output. Carry output is directly. You can see this. Carry output is directly XGY. I'll just zoom it if it is not visible. Okay. XGY is a carry output. Then input is A, input is A, input is B, and carry input. So carry input is not needed because in full adder it was there, but it is not needed here. Let me force it as 0. So this is a full adder. So what I did, I took this block, and here one more thing, important thing, I should have done it. That is, here I should have forced it as 0. So not needed. Okay, just not needed. In my this explanation, wherever I explained, there is no carry input, so I just force it to 0. So what I do now, it is 0. Now next, XGY is already done. Now what I have to do? X equal to Y. So for X equal to Y, I need a AND gate. AND gate primitive is there. So its output is XCY. What are the inputs? This all 4 bits of the sum expression. So and let me give the label as A1. So what is the output? Output is XEY, comma XEY. This is the output. What are the inputs? The 4 bits of the sum expression. What are the 4 bits of the sum expression? I have used the intermediate. Yes, this is the 4 bit of the sum expression. Let me write it in this manner. Yes of 3, sorry, S of 2, S of 1, S of 0. Okay, this is AND gate. XEY is also done, XGY is also done. Now last is XLY. XLY is NOR gate of these two things. That's it. So I use a NOR. Let me label it as N1. First output is XLY, not X. Actually here it is A, right? Somebody should have alerted me. This is A, this is B, this is A, this is B, right? So in the block diagram, we had considered it as A, X and Y. Here it is A and B. So that's it. ALB. So what are the inputs? AGB, comma AEB. That's your inputs. That's it. So this is a code for the comparator 4-bit. So save it and set it as a top level module. Set as a top level module. Yes. Okay. So now I synthesize it. Let me synthesize it. So it is taking some time. So there are some errors. Let us check what are the errors. Um, line 27 syntax error. So line 27 syntax error may be because of this one. So let me force the logic 0 as one tick B 0. For me, I work both on VHDL and Verilog. So because of that, some confusions between the syntax I'll face because I work on a lot of programming languages. And VHDL and Verilog being almost same, the the constructs are different. Let me see if it works. It's getting synthesized. Yeah, synthesis is done without any errors. The synthesis is done. Now it is writing the stimulus block. So there is no stimulus block is written for that. Um, Let me just take new new source, Verilog test fixture. Let me write stimulus for comparator, and select that you need to test a comparator. Next, finish it. Okay, wait for a while. So stimulus block got opened. So this I did not prepare it and keep. That's why it's taking time. I hope it's a revision for you. So you can see that inputs are registers, outputs are wire, and this is by default. By default, it will get it instantiation with a design unit. Initial a equal to 0, b is equal to 0. Okay. So similarly here, you can just give a is equal to 8, b is equal to 4. Okay, then I'll give all the test cases here. A is equal to 2, then both same, then I'll finish it. Dollar symbol, finish. Okay, so end and end module. So I'll save it, save, and I'll go to the simulator. So I'll select the just stimulus underscore comp and run it. Okay, this is how the stimulus block is written. You can do it in any ways. Okay, you can use monitor statement, display statement, do anything, whatever is your wish, because the coding can be learned only by doing experiments and trying different ways. There is no straight formula for writing a code. Simulate behavioral model is successfully completed. It is taking some time. Yeah, zoom to full view, and let me just keep it as unsigned decimal. Okay, so here a is equal to there is some mistake here, you can check. A less than b, a less than b is there. There is somewhat somewhere something has gone wrong. We shall verify it. A greater than B should be 1. Oh, big mistake we have done. I just identified now. I just expect some students to correct me if I go wrong. No student is doing. You can see here. There is a complement to be put here. For B, everywhere there is a complement that we have not done. That's where we have went wrong. Okay, that's a big mistake we have done. So here complement should have been done. So complement we have not done. So this thing, if you miss, then you observe that. Think that these errors are good because it will give a lot of learning, and live simulation will help you in in understanding this. Like even your teacher can go wrong by over viewing or over seeing it. So I forgot to just complement it. That's why there is it is just adding acting as a adder. But the problem is the logic is like you need to understand that where you went wrong. So here it's A is a 4 bit. You already know A is 4 bit. B is also 4 bit, but it is down to 0. So that's why I took individual inputs B3, B2, B1, B0, everything I complemented. Again, I need to repeat all the process. So go to implementation, comparator, synthesize everything, again. Go to stimulus block, give there. So that's how you need to do. So I hope all of you are there. Yeah, it's you're there. Anybody who has told? No comments I've received. I think nobody of you have noticed it. So there is some error. Full adder expects 5 arguments. Uh, of course, there are 5 arguments. Full adder expects. There is an error here. 1, 2, 3, and there is a 5 argument here. Uh, Let me just try it with this method. Um, Logical operator. So if you remember the logical operator, so logical operator is not logical operator, bitwise operator. So this is inversion, correct. I think it does the work for me. I am running out of the time. Which is your next class? Anybody please put it in the chat box. I'm running out of the time, or else I can just show it in the next class. If you have time, I'll just continue. Please come up in the chat box. If you have any class, you have control system class. Okay, then uh, fine. So let me keep this code for the next class. Synthesis is done. So only thing is the mistake was here. I did not invert it. So if you just run the simulation, the work is done. So I think you can bear with me for another 2 minutes. Okay. So to avoid such simple things, errors, I'll keep everything ready before the class starts. Sometimes it happens, and when I'm running my computer with heavy duty, so it takes a lot of time. Let me check. This is A equal to B, so A equal to B. This is that radix unsigned decimal. So 8 is greater than 4, so greater than 4, and A is less than B, AL is less than B. A is equal to B, so A is equal to B. So everything is perfectly working. I hope there are no doubts. So please come up in the chat box if you have any doubts. I have only 1 minute of time soon. Finally, we concluded it. Okay, this completes your the second unit. Okay, so if you have any doubts, please come up in the chat box.